let me just try it out side by side.
No worries. Still got a few minutes.
It's time?
Yeah. Okay. So this, just put it under your chin somewhere.
Yeah.
Yeah, that's perfect. This goes in your pocket.
Yeah.
I believe. Do you want to give it a try?
Yeah. Can you guys hear me?
Yeah.
Okay.
Good.
Yeah.
All right. And
I'll just.
okay, everyone, let's welcome Ravi Shankar
Yep.
with the Thin Arbiter from glusterfs.
All right. Thank you, guys. Yeah. So my name is Ravi Shankar. I'm a senior software engineer with Red Hat. I've been working with glusterfs for about 7 years, mostly on the replication component. But I've also worked on other areas of Gluster like the CLI, the Gluster daemon, and the POSIX translators. So anyway, so this talk is mainly about Thin Arbiter for glusterfs replication. So the agenda for today is I'll spend the first few minutes on the first 3 bullet points where I talk about what the glusterfs architecture is and how it achieves replication using the automatic file replication or AFR translator. And then we will discuss how quorum logic is important in preventing split brains when you're writing to files from multiple clients. Once we have an idea of these 3 things, then we can actually go to the topic, which is Thin Arbiter for glusterfs replication. Right, so this is the architecture of Gluster. So on the right hand side, you see many green boxes. They are all servers, server 1 to server n. Each of these servers host a glusterfs process, which is composed of many translators, like it starts from the server and down with POSIX. So all of these servers are connected together to form a trusted storage pool, and this is what the volume is comprised of. And on the right hand side, you have the client, which is basically accessing the volume via different mechanisms like Fuse or NFS Ganesha, or there's also a libgf API binding where you can write your own application using those bindings to access the volume. So most of the logic in glusterfs is done by translators. So each translator has a specific job. The replication translator sits here on the client side, and it has many children. So depending on the replication factor, each client talks to the respective bricks and it does the replication. So the synchronous replication in Gluster is mainly client driven, meaning the client connects to all the bricks and the updates are sent synchronously to all the servers, and we wait back for the responses from all the servers before sending back the response to the application. So it follows a strong consistency model, unlike geo-replication where the consistency is eventual. Here, the moment you do the write, because we propagate it to all the servers, you get the writes immediately on the disk. And the writes follow a transaction model because you also have multiple clients accessing the same file, and you need to have a transaction to prevent, stale data or like partial writes going from one client to one brick and the other client to the other brick. The reads are served from one of the replicas, and the slowest brick also dominates the write for performance because we are binding the writes to all the bricks. So there's also a feature of self-healing, where when an update from a client does not go on all the bricks, the self-heal daemon keeps track of what files need heal, and when the brick comes back up, it automatically does the healing. So to that effect, you have CLI commands to monitor the status of the pending heals, and you also have commands to resolve split brains in case of replica 2. So I was telling you that the write follows a transaction model. So there are basically 5 steps for a write when a client does a write. The first is the lock. So lock is when the client takes the lock on all the participating replicas. You need to do this because there are multiple clients accessing the same file, and while doing the write, you need a lock to prevent out of order writes. So once you get the lock, then you do something called the pre-op. It's basically a set exciter call that's done over the wire. So you mark an exciter on the file saying, hey, I'm about to do the write. Let's mark something called a dirty bit. So then after that, you do the actual write operation, and if the write is successful, you remove the dirty bit, and then you clear the dirty bit. And if the write transaction fails on some of the bricks, then the good bricks will actually mark another extended attribute on the bad bricks saying that there is something pending heal, and so that when the brick comes back online, it can start healing. And then finally, we do the unlock. So the reads are very simple. It's just basically serve the read from one of the good bricks. So AFR uses the extended attributes to know which is good and which is bad brick. So reads all are always ensured that you always serve from the good brick. So which brick does the read get served from? That's configurable. You have various policies. So the default policy which is used is the hash of the GFID of the file. So that means that even though there are multiple clients, if they are accessing the same file, they will go to the same brick. But you can also load balance it using other strategies like mixing the hash of the GFID and the client PID. The client PID is unique to each client, so you can distribute the reads too. So the self-heal daemon I was telling you was is the responsibility of the self-heal daemon to ensure that the missed writes are actually healed onto the bricks when they come down, when they come up. So the self-heal daemon runs on every node of the cluster, and it heals both data, metadata, and entries that were missed when one of the bricks were down. So there are two ways to do the heal. One is to crawl the entire file system, right? That's like a really stupid way of doing it. So what AFR does is it maintains the list of failures in a special directory called indices.glusterfs indices folder. So whenever a write transaction fails on some of the bricks, the good bricks record these GFIDs inside this .glusterfs folder, and when the bricks come back up, the self-heal daemon crawls this folder and it just gets the list of files that needs to be healed, and then it does the heal. So the self-heal daemon does the healing under the presence of locks, because clients can also be writing to the same file when the healing is going on. So you will have to take logs for mutual exclusion from the client IO. So the traditional way of replicating had been earlier replica 2, but the problem, as you guys might already know, is that replica 2 is prone to split brains. So there can be two types of split brains in time and space. Split brain in time is when the write from the same client succeeds on one brick and fails on the other, and the next write succeeds on the opposite brick. So here we have brick 1 success, brick 2 failure. Here the write on the brick 1 failed and the brick 2 succeeded. So when the both bricks come back up, the client doesn't know which is the good copy and you cannot resolve it. And the other one is split brain in space, where clients can partially see the bricks. So there are two clients, say client 1 and client 2. Each of them can see only one brick, and you still allow the write because there is no concept of quorum in replica 2. So you can end up in a split brain in that state also. So how do you avoid split brains? You have to have a notion of quorum, which means that you need to go at least for replica 3, or basically odd number of replicas. So the general thing is that for a 2n plus 1 replica, you can at most tolerate failure of n nodes. So that means if you have a replica 3, you can tolerate failure of one node which is going down. So the thing to note here is that just because you have replica 3 and 2 nodes online, you cannot say that you are always guaranteed to serve a read. So there is a problem that if the only good brick which had witnessed all the writes goes down, then you still have to fail the IO. So let's just look at that with a diagram. So here you have client which is trying to write to all the 3 bricks. The first write did not succeed on the third brick, and the second write did not succeed on brick 2. So now we have brick 1, which is the only one which has witnessed all the writes. So when the third write comes, even though the client is connected to brick 2 and 3, we cannot allow the write because the only good brick which witnessed all the writes previously, that is brick 1, is down. So that's one of the things in any replication system. So even if you have quorum number of bricks, if the good bricks are down, then you cannot still serve the reads. So you guys must have already used or known about arbiter feature also. So arbiter was also a type of replica 2 plus the third brick is used as arbiter, where it stores only the namespace. It doesn't store the contents of the file, so they are all 0-byte files. So I was telling that AFR uses extended attributes to figure out which brick is good and which brick is bad, right? So in case of replica 2, because there are only 2 copies, you cannot store the exciters. You don't have 3 copies of the exciter. So the arbiter kind of overcomes that problem by storing the file name alone. So only the namespace is captured, and you store the exciters on those respective files. So now, since we have three copies of the metadata information, we can prevent going up in a split brain state. So this was the arbiter. So why did we go with the thin arbiter? So let's see what the thin arbiter is. So thin arbiter is essentially a replica 2 volume plus a lightweight thin arbiter process. So if you look at the normal arbiter, it's actually a full-blown process in the sense that there is one arbiter for every replicate subvolume and it stores all the files of that particular volume. But thin arbiter is not like that. It is actually lying outside the trusted storage pool, which means that it's not a part of the cluster at all. So you can host this in a cloud environment somewhere where the management daemon of gluster-D is not running at all. So the node is not appear and it's not running and it's not managed by gluster-D. So if you look at the volume information, you will still see that it is depicted as a 1x2, which is a replica 2 volume, but you'll also see an extra line called it's a thin arbiter. So that's how you'll identify that the volume is a thin arbiter volume. So thin arbiter can be, the advantage of thin arbiter is that you can host multiple replica 2 volumes with the same thin arbiter node. So you have, if you look at the diagram here, you see that there are different trusted storage pools. You have TSP1, TSP2, and they host different volumes. Some of them are thin arbiter volumes, some of them are normal volumes, and they all use the same thin arbiter, which can be hosted separately in the cloud. So all the clients which are in the respective, which access the respective volumes also talk to the thin arbiter. So one caveat here is that we must use volume names which are unique across the different trusted storage pools. So the reason is because the thin arbiter has some ID file, which we'll see in the next slide. So that uses the name of the volume to identify which replica it belongs to. So if you have the same volume name across multiple trusted storage pools, then the thin arbiter ID file uniqueness is lost. So that's why as long as the volume names are unique, you can use the same thin arbiter for multiple storage pools. So what exactly is the thin arbiter process? So it is essentially a lightweight brick process. So you have all the standard translators which you see in the glusterfs brick process, like starting from protocol server and ending with the POSIX. But you also have one additional translator called the thin arbiter here, which is sitting just above POSIX. So I was telling you that the thin arbiter contains only one file, and that file is used for quorum to determine which brick is good and which brick is bad, right? So the only operations that come on the thin arbiter are first creating the ID file, which happens only once during the life cycle of a volume, and then the actual set etc calls, which AFR uses to track which brick is good and bad. So any other op which comes on this has to be like barriered. So that's the job of the thin arbiter translator. So it allows only the create and the etc op to go through. Anything else would be barriered. And the other thing is that the thin arbiter, I was telling you that you can run thin arbiter process on a node which does not have gluster-D. So if you know gluster-D, gluster-D is a management daemon which is used for spawning all the brick processes, the cell field daemons and all that. So if you restart a node, it is gluster-D which ensures that the brick process comes back up. So without gluster-D, how does it actually work? So if you have mounted a gluster volume, you know the way the mount logic works is when you issue the command mount -t, blah, 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 the server name and the volume name, the client initially talks to gluster-D and gets the information about the vol file and then connects to each of the bricks using a particular port number. But because thin arbiter node, we are not hosting any gluster-D brick process, so we are not hosting any gluster-D process, we need to hardcode a port number. So we currently use 24007 because that's the port of the gluster-D. So because gluster-D is not running, when you mount the volume, the client will directly connect to this thin arbiter process on this port. If you want to change it to some other port, there are volume options available. You can configure it using a different port. So let's look at how thin arbiter works for writes and reads. So let's assume that the application is writing something on file 1 and you have brick 1, brick 2 and thin arbiter. And let's say the write failed on the second brick and succeeded on the first brick. So what AFR does is, before sending back the response to the application, it marks on the first brick that there is some pending operation on the second brick. So it essentially marks that brick 2 is bad. So that information is marked both on the first brick and also on the thin arbiter. So after marking that, it also stores in memory that which brick is good and which brick is bad. The reason why it does is because thin arbiter does not need to be in the 5 millisecond latency limit which is there for normal gluster brick processes. So in order to not contact Thin Arbiter for every file operation, you try to maintain in memory the information about the bad brick. So the client says that in memory that brick 2 is bad, and then it responds with success to the application. Now when the write 2 comes on the same file, as long as the write succeeds on the previously known good copy of the brick, we say that it is a success to the application. So if you look at the diagram from here, write 2 comes on file 1 and it succeeds on the second brick, but succeeds on the first brick but fails on the second brick. So because we already know from the previous write that brick 1 is the good copy and brick 2 is bad, we can return success to the application without actually contacting the Thin Arbiter. So that's how it's not actually participating in the IO path. So let's see what happens when a write comes and it fails on the opposite replica. So write 3 comes on the same file, and this time it fails on the first brick but succeeds on the second brick. Now because we know that if we allow this as success, we can end up in a split brain state. So we don't return success and we actually fail the FOP. So this is the essence of Thin Arbiter. So to summarize like how the write works, so if the write fails on both the data bricks, then you can obviously say that the write failed. If the write fails on one brick, and if it is already a known bad brick, then you can return success to the application. But if the write fails on the brick which is already good, then you'll have to fail the application. All right, so let's look at how reads work. So let's look at each case. So in the case when the client is connected to both the bricks, so when we have this state, let's say that we already are in a state where the brick 1 is marking the brick 2 as bad. So brick 1 is good, brick 2 is bad, and the client is connected to both the bricks. In this case, we don't have to query the Thin Arbiter because the AFR exciters on both the bricks already tell us which brick is good and which brick is bad. So you don't have to actually contact the Thin Arbiter to know whether your results that you interpret from the exciters are valid or not. You can trust them and you can serve the read. The only problem or the only reason that you need to contact Thin Arbiter is when before that let's go to the second case. So case 2 is when we have the client connected to the good brick and it's disconnected from the bad brick here. So if this good brick already blames the second one with an exciter, then we can be sure that you don't have to contact the Thin Arbiter node because the exciter status node and the exciter here already is blaming this guy. So you can directly allow the reach to go through. But let's say the client is connected only to this brick which is bad and not to the first one which is good. So if this guy doesn't blame anybody, we cannot blindly state that I'll serve the read from this because this does not contain any exciters. This does not contain any exciters. You will have to query the Thin Arbiter. So that is the case where the client actually has to query the Thin Arbiter, and if the Thin Arbiter doesn't blame the brick which is connected to, then you can serve the read. Otherwise, you will not be able to. So to summarize what we discussed in the previous slide, if both the data bricks are up, then you serve the read from a good copy. Both can be good. If one of them is down, then you will have to query the brick which is down. Which is up. And if it doesn't blame the brick which is down, then you can surely serve it. But otherwise, you will have to contact the Thin Arbiter and get the information from the Thin Arbiter to see which is good and which is bad. So the next 2 slides are a bit of an implementation detail. So I was telling you that the client maintains in memory which brick is good and which brick is bad, right? So the self-heal daemon actually also heals the files when the bricks come up. So how does the client invalidate its in-memory information when the self-heal daemon heals the file? So for that, it makes use of upcalls. So the logs translator in glusterfs provides this notion of an upcall for logs. So when there is a conflicting log from another client, the logs translator will send a notification to the one which is currently holding the log, and it is up to that client to release it so that the conflicting client can take the log. So and there is also logs translator also supports taking log on the same file from the same client on multiple domains. So for example, client 1 can take a lock on file 1, say from offset 0 to 10. On domain 1, it will be granted. If it is trying to get the lock on the same file using a different domain, it will still be granted. So the locks translator has this distinguishing feature of domains, wherein if the offset and the range of a lock on a given file is same, but the domain is different, you will allow the locks to go through. So AFR actually uses these two features to invalidate the in-memory information. So we'll see how that works. So when the first failure happens while writing from a client, during the post-op phase, AFR takes two locks, one in the notified domain, another one in the modified domain. Then it marks on the thin arbiter saying that this brick is good and this brick is bad. After doing the marking, it releases only one lock, which is in the modified domain. So the notified domain lock still resides in the thin arbiter. So for every client that is connected to Thin Arbiter, you have a bunch of notified domain locks which are residing in the brick process. So how is that used is what we'll see. So when the self-heal daemon starts to heal the files in the volume, it will attempt to take both the notify and the modify locks. And because of the lock contention feature available in locks translator, it will send an upcall notification back to the client. So if there are ongoing writes in the client, it will complete the writes and then release the notify lock. So then the self-heal daemon can actually get the lock and it will proceed with healing the file. So the thing to note is that if IO fails during the heal, the client will again mark on the bad brick saying that and it will basically invalidate its in-memory information. So this is how locks translators, upcall infrastructure, and multiple domain locks are used for maintaining the in-memory information. So installation and usage is pretty simple. So on the Thin Arbiter node, you'll have to install the server RPMs and you'll have to run a script to start the Thin Arbiter process. Once you have that done, then you can peer probe and create normal volumes, which are replica 2, and use the syntax called gluster volume create. I'll show this in a demo. So if you are using it in a standalone mode, you can use this method. If you are using containers and if you are using a provisioner for containers, there is something called cuddaloo.io, which is also provides support for Thin Arbiter recently. You can try that out. So the things to do that are there is we currently do not have support for add brick and remove brick CLI. So if you have used gluster volumes, if you want to like replace a brick or convert existing replica 2 or replica 3 to Thin Arbiter volumes, it is currently not possible. So those are the things that we need to work on. So the reads also, I was telling that, so the writes have in-memory information on which brick is good and which brick is bad, but the reads do not have that information. So every time it queries the Thin Arbiter to get the information. So that is something which we need to work on to optimize the information about using the in-memory information about the bricks. And you also have to fix bugs. If you guys try it out and report bugs, we'll be happy to fix them. So I'll just show you a demo now. I have recorded it already. I'll just play it out. So we have, I hope the font is visible. So we have 4 VMs here, like 1, 2, 3, and 4. Ravi 1 and Ravi 2 I'm going to use for hosting the actual volume, and Ravi 3 I'm going to use for hosting the Thin Arbiter process, and the 4th machine would be the client. So let's first start with installing the Thin Arbiter on VM 3. So you have to run the script called setup-thinarbiter.sh, and you have to run it with the -s flag. So it will basically ask you the brick path, and you enter where you want the brick to be hosted. You say brick TA, and then the Thin Arbiter has been started. So if you check whether the process is running, you can see it. And I was telling you that there is no gluster D on the Thin Arbiter node, which means that the process management has to be done automatically by systemd. So we have integrated this with systemd so that even when the Thin Arbiter node gets rebooted or the process crashes, it will automatically start it. So the unit file takes care of that. So let's try to kill the process and see. You can see that it is again spawned again with a different PID. So you don't really need gluster D on this node. So having started the Thin Arbiter, let us try to create a replica 2 volume using the first 2 VMs. So I'll just export some environment variables with the IP addresses of the VMs, and then I'm going to create a Thin Arbiter volume. So the syntax is cluster volume create vol name replica 2 Thin Arbiter 1, and then you give the list of bricks which form the data bricks of the volume, and in the end you mention the Thin Arbiter. So VM3 is the Thin Arbiter here, so we say VM3 bricks brick TA, and that's it. So we'll start the volume. Okay, so now let's see on the second node whether the bricks are up and running. It is. So now we are good to actually mount the volume and start doing I/O on it. So we'll go to the node 4 now. So before mounting the volume, let me just show you the ID file. So if you look at Thin Arbiter, it's currently empty. There is nothing here. So I was telling you that the ID file is created when you first mount the volume. So if you go issue the mount command and then come back and check here, there is this ID file which is created. It's a 0-byte file, and this ID file is used for capturing the good and bad brick information for all the files in this replica subvolume. So if you do a write to a file, you see that the file contents are getting replicated to both the bricks of both data bricks. So let's kill one second data brick and try to write something. So the write is successful, and you are also able to read it, because now this is the only bad brick. So if you now look at the extended attributes on the Thin Arbiter, if you do a getAffector and see, you will see that it contains certain extended attributes which blame the client 1. Client 1 is the second brick. So client 0 is first and client 1 is second. So because we killed the bricks in VM2, it is saying that there is a pending data heal on the second brick. So the Thin Arbiter essentially captures this information. And the client also has it in memory that now the second brick is bad and I should not allow any writes which might fail on the first brick. So let's kill the first brick and see what happens. So now we are going to kill the brick which is good, and we'll bring the second VM back up. So now you see that the first brick which witnessed the write was killed, and now the second brick is up. But even now when you try to access the client, you will see that the clients fail both reads and writes. So ls reader fails with input output error, and writes also fail with input output error. So because the only good brick is down, we are not allowing the writes anymore. So if we bring the brick back up, so we'll restart glusterd on the first node so that the brick comes back up. Now the self-heal daemon would have automatically healed the file by now, and you can see that the file is again accessible from the mount. Yeah, and if you look at the Thin Arbiter extended, before that let's look at the contents of the file on both bricks. Yeah, so the contents of the file is also the same on both bricks. And if you do a getAffector now and look at the extended attribute that AFR maintains, it's now reset it to all zeros. So earlier it was like blaming the second brick. Now because the self-heal has happened, it's reset it, and now you can continue with the IO as usual. Yeah, so that's pretty much it. Guys, have any questions? All right then, thank you. Thanks.
I think I was a bit fast.
Yeah, I was just going to put the 15 minutes.
Yeah.
So that's okay. A lot of talks are fast. So I'll give some instructions as well. You have the white lines to take. This is on the video. It's the video. The slides are correct through the box. Record it on the box. Then put here. So if you stand in front of the screen, you will not be recorded. Okay. City blue. Yeah, what's good? Oh, but that has no. Yeah, okay. You have enough time. Yeah. I think let's skip for now. If I need it, I will put it on charger by then. Don't forget. Let's do each question and let's do half of the mic. We have assigned to the quick question as well. Okay. Remind you. We do forget. Okay. If you want to announce questions during the talk, or so you just mention it in the introduction or something. Once you have a question, you have to look at it. Either way, it's better better so the audience might ask questions and if you don't want them and you have what do you use?
They claim bulk storage.
Yeah. If you can ask, so arrow next to it, okay. I think there might be an option for the little arrow next to it. So, there we have. So you can put this screen on yours. Yeah, so then you have both. You put this in full screen. Yeah, you just press F11. F11 so they don't. Okay. Yeah, now you have to go back to the. That's okay. Probably this time it makes it easier for you. Yeah, I just finished with the audio. That's great. You do have the slides there as well. So you know, on the screen, if you watch like this, also you can. Yeah, so whenever you prefer. I want to start it right now.
No, you have to wait until.
The time happens.
Yeah. So it's another 15 minutes.
Okay.
So you want to have the mic already?
I think I'll skip it. You can put it. I'll take it later on. Because
Okay, because you have.
15 minutes. That's all.
Yeah, exactly. So, yeah. So the mic is mostly for the recording. Even if you speak loud enough, the room might understand. But, yeah.
Okay.
5 more minutes.